here
Okay.
before we can start. Just hold on a moment. Is he showing? Okay. So I think we're able to go now, Jane. Are you happy that we launch? And Tim, I'd like to just introduce you. I don't know if you were attending the last bit. It'd be great if you're around for the discussion and summary, but it sort of set you up a little bit with these long, fat tails and things. You're going to be talking about, I think, uncertainty quantification, the role of uncertainty in weather and climate. And may I also tell the audience before you do that you're close to publishing an interesting book, which is called The Primacy of Doubt. I think it's with OUP. I just sent you a few figures for that, which I hope you received. And it's over to you to talk. I'll tell you when you've got 5 minutes to go, all right?
Yeah, great, brilliant. So just, you can see the opening slide, I guess, can you? Hello, can you see the slide? Can you hear me?
Yes, it's very clear now.
Okay.
Go ahead.
All right, brilliant. I noticed that tomorrow Dave Sexton from the Met Office is talking about climate change projections. So I'm going to focus mostly on the weather timescale, but I'll say a few things at the end about climate. And I think, you know, I've been listening in since the beginning of the meeting. I think there are some clearly points of sort of contact and similarity between the meteorological community and the epidemiological community. Well, actually, one thing I'll just say is this year marks the 30th anniversary of the introduction of ensemble forecasting into weather prediction, something I was closely involved with from the early years. And I thought I would actually just start with the situation as it was, let's say, back in the 1980s in meteorology. We were aware, of course, of Lorenz's great work on chaos and the fact that the weather is a chaotic system, and that means you can't predict, you know, in detail arbitrarily far ahead. But this concept arose out of Lorenz's work and other pieces of work, that maybe there's a kind of a limit of predictability within which you can make deterministic predictions, and maybe beyond which you can only make probabilistic predictions. So the situation in the sort of 1980s was that sort of up to about 2 weeks, it was possible to make deterministic predictions, and beyond that, one would need some kind of probability theory. And you know, that's, you can view that this picture of the two trajectories from the, or two time series from the Lorenz model, you know, they start, if that's a kind of a typical type of time series, you can see that the two start to decorrelate after the red line, and that in the atmosphere people sort of think of as, let's say, 2 weeks, roughly speaking. I used to argue with my colleagues that that was a bad way to think about weather, and certainly a bad way to think about the Lorentz model, because if you look in detail, you see that how errors and uncertainties evolve depends very much on where you are on the Lorentz attractor. So you can get, like the top left-hand diagram shows, you can get periods, places on the attractor where the system is actually extremely stable, and that small uncertainties in fact decay rather than grow. And then conversely, at places near the bottom middle of the attractor, the uncertainty explodes just in a very short period of time. I mean, one can expect this generically because one's dealing with a nonlinear system. So if f on the right-hand side of the equation, top equation there, is a nonlinear function of x, then it means that the gradient of f with respect to x is at least linear. So if f is at least quadratic, then f is at least linear. Sorry, df by dx is at least linear. And that means that small perturbations, the growth of small perturbations will depend on where you are on the attractor. If df by dx is not a constant, if f is a nonlinear system. So we can expect this generically, and I would argue in most of areas. I mean, famously in economics, I think we see, you know, periods of extreme instability and meltdown. We see it actually in looking at the motion of planets. You can get periods of stability mixed with periods of extreme instability. And possibly also in epidemiology, something similar happens where you get periods of instability. The whole point then about ensemble forecasting, this is the number one raison d'etre for, in meteorology at least, is to be able to identify those explosively unpredictable situations ahead of time. Now, my colleagues in the 1980s were kind of skeptical that this really was as important as I was claiming. Fortunately, nature dealt me at least a kind of a trump card, which, at least in the UK, was perhaps the most famous misforecast of the 20th century by Michael Fish on the BBC TV in October 1987, where he said famously, hurricane, what hurricane? And there was indeed a hurricane the next day. So we retrospectively ran an ensemble of 50 forecasts for that period. And what we're looking at here is the surface pressure maps 2 days, 2 days before, that started 2 days before the hurricane hit. And what it shows is an extraordinarily divergent set of predictions. So normally if you run an ensemble and look at the surface pressure 2 days ahead, 99 times out of 100, the 50 surface pressure maps will look almost identical. They'll differ in terms of exactly where the rain bands are and so on, but the pressure maps look very similar. But this is a case of explosive instability and sort of captures that example of in the Lorentz attractor pretty well. So that actually, I would say, if anything, kind of opened the door for an operational implementation of ensemble forecasting. It was an October storm. Now, one question, you know, to ask is, how do you actually communicate? I mean, you can't give the public 50 forecasts. That makes no sense. How do you communicate that sort of information? And I have to say, you know, one often sees in other disciplines a lot of focus being put on the fact that if you average an ensemble together, you know, it can have a smaller, lower root mean square error than, say, any of the individual forecasts, and that's correct. But you throw out the baby with the bathwater by taking an average over all the forecasts. In this case, you just completely lose the fact that in many of the ensemble members you have an extremely intense vortex by just averaging the 50 together. Averaging just produces a very insipid meteorological field. It's not actually a solution of the equations of motion. So the way to deal with this problem is to disseminate probabilities of things that you think are important, and in this case, hurricane force winds would be clearly a relevant quantity. And if you do that from that ensemble, you see a map like this where you get probabilities of 30 or 40% of literally hurricane force winds. And, you know, if you remember, is it My Fair Lady, where it said that in Herefordshire, Hertfordshire and Hampshire, hurricanes hardly ever happen. 30 or 40% is really quite a large probability, climatologically speaking. So I just make that important point that we rarely use ensemble mean forecasts when we're looking at ensembles in weather prediction. And, you know, this whole kind of dichotomy, if you like, between predictable, semi-predictable and unpredictable, you know, works around the world. It works for tropical cyclones and hurricanes. This was an example, the top of a cyclone that hit Bangladesh, very predictable a week ahead. The middle one was Katrina, the famous one that hit New Orleans, which actually was at a range of a week ahead, was actually quite unpredictable. And then you can get situations like the bottom one, which are just spectacularly unpredictable. So again, very similar to the Lorentz model kind of paradigm. And well, as I say, the ensemble went operational in 1992, and it's been a slow kind of advance forward in getting people to use it. But really now it's become kind of center stage. And one of the most exciting areas, I think, of the application of ensemble forecasting is in what's called anticipatory action. And, you know, I'm sure everyone's aware of the fact that traditionally the disaster relief agencies tend to only move into areas once they've been hit by a hurricane or some, you know, major flood event or something like that. And of course, that's very frustrating because all the communications are down, the roads are down, people are devastated, and it often takes days, if not weeks sometimes, to get the, you know, food, health, water, medicine, bedding, and so on into place. So now the idea is that the humanitarian agencies, they have what they call probabilistic triggers. They say, well, if an event is predicted with a greater than a certain threshold probability, which they determine what that is, then they actually take anticipatory action. They move the beds and the food and the medicines and so on into place before the event hits. And this has been a real sea change in the way in which disaster relief and humanitarian aid works in the world. And it's a revolution that's sort of happening as we speak. I thought I'd just show a couple of slides on how we typically validate an ensemble forecast. You know, there are many such things, but I'll just give two examples. Again, I want to focus on the fact that we don't tend to use the ensemble mean scores very much because the ensemble mean is often not the most useful forecast because of the problem I mentioned. So things like reliability, what's called reliability diagram. So what that means is if I predict an event with 80% probability, I should expect over a sample of such occasions the event to occur 80% of the time. So we're looking to see that probabilities and frequency of occurrence are calibrated. And the top diagram is from the ECMWF ensemble, which I've worked with since the early days, for surface temperature, different thresholds. And you can see, broadly speaking, the ensemble is reasonably reliable. In other words, you can see it's not actually plotted on a square, but you can see the sort of diagonal as a thin gray line that ideally the curve should lie on. You can see they dip below the diagonal when we get to very high probabilities, indicating that actually, even now, we're still missing some uncertainty in the representation of what we consider to be, or the ensemble considers to be extremely probable events. And well, we believe that's mostly associated with the fact that we don't yet have a good representation of uncertainty in the land surface models at ECMWF. So that's work for the future. And then the bottom one is a thing called potential economic value. It's a kind of using a simple decision theoretic model for deciding, you know, a potential user would decide whether to take precautionary action or not. And it's based on the idea that there's a cost to taking precautionary action. But if you take precautionary action and some weather event occurs where you would incur a loss, L, then based on your cost-loss ratio, you can use the ensemble probabilities to decide whether to take precautionary action. And this shows the potential economic value of the dotted line shows the ensemble value, and the dashed line shows a higher resolution ensemble than the ensemble itself, which actually has lower potential economic value. For people who know what the Breyer skill score is, the Breyer skill score is essentially the area under these curves. Okay, now I want to just talk a little bit about, you know, how are ensembles created, because it's actually not straightforward. You know, people naively say, well, we've got initial conditions which are uncertain, and we've got model equations that are uncertain. And we can kind of add some stochastic noise to the initial conditions, and maybe we can add some stochastic noise, sort of independent stochastic noise to the model equations, and generate our ensembles that way. If we do that, we'll end up with extremely underdispersive ensembles the probabilities will be very overconfident and completely unreliable for decision making. So by far the hardest piece of work in the generation of the ECMWF ensemble was how to produce the perturbations for the initial conditions and model equations. And this relates to a point that actually was made a little bit earlier in the context of data assimilation. But let me just say very briefly, we're dealing with here partial differential equations. We solve them on a computer by discretizing these partial differential equations like Navier-Stokes. So we have a grid on which the equations are projected, and then we have what are called subgrid parameterizations to represent processes like clouds or orographic gravity waves, turbulence in the lower boundary layer, and so on and so forth. Lots of processes which can't be resolved. And these are represented by simplified formulae which have free parameters. Now, at some level, uncertainty arises because of this discretization process. And we could say, well, okay, maybe the form of the parameterizations, maybe the precise formula is uncertain, maybe the parameters are uncertain. And that's true. Some of the parameters are uncertain, some of the formulae are uncertain, but there's actually something deeper that is uncertain. And I want to dwell upon that because that really characterizes I think in the last talk, the difference between parameter uncertainty and what you might think of as structural uncertainty. And I just want to just briefly kind of go through the question, well, what do we mean when we talk about parameterizing something? We're kind of driven by analogies with statistical mechanics. We can talk about molecular viscosity by a simple formula or molecular diffusion by a simple formula because there are so many molecules within a small macroscopic volume, Avogadro's number. And that philosophy determines in a way this structural form for weather and climate models. We treat the subgrid processes like a statistical ensemble of clouds, for example. We have a statistical ensemble of convective clouds, thunderstorm clouds. This is the idea, at least, and that enables us to create a kind of a bulk formula for these thunderstorm clouds, which describes not any one cloud, but the ensemble of clouds within a grid box. The problem is the real world isn't like that. In fact, it's precisely because of the Navier-Stokes equations, what's called the scaling symmetries of the Navier-Stokes equations, which give rise to power law structures for turbulent energy in the atmosphere. We actually don't see a single kind of cloud system at one scale. We see a whole spectrum of clouds at different scales going right up to the grid box scale. And it's really the violation of this scaling symmetry by truncating the partial differential equations that's the fundamental reason why we have uncertainty in our computer models. So the point is this, that it's not so much that the formula is uncertain for the parameterization or the parameter is uncertain, but the whole concept of being able to parameterize in the first place is actually uncertain. At ECMWF, we deal with this with stochastic types of parameterizations, but here the stochasticity is not just some additive stochasticity, it's a multiplicative stochasticity. I don't have time to go into this in detail, but multiplicative stochasticity on total tendencies of temperature and vorticity or wind speed. But this doesn't actually solve the problem. This kind of alleviates the problem to some extent, but it doesn't solve the problem of how to represent model uncertainty. And I would say actually it's still an unsolved problem. And this feeds into, and it was interesting some of the discussion earlier, because this very much feeds into the issue of data assimilation. As was discussed, I think, in meteorology, we assimilate observations into models by typically minimizing some objective function. So, we might start with a first guess forecast trajectory, and then some observations come in, and then we do a kind of minimization to find a new model trajectory. So this is a solution of the model equations which fits both the observations and the prior guess in an optimal way. Now, a critical issue here in data assimilation is to do with how coarse the model grid boxes are. Because if the observations are being influenced by processes like cloud processes or thunderstorm processes, which the model can't resolve because it's too coarse in scale, then the model is not going to be able to assimilate that information from the observations properly. And indeed, how to represent that problem of how information from observations is mishandled in a data assimilation process where the models can't resolve the information in the observations is still an unsolved problem. And one of the most important, yes,
just
hello.
to say, you have a little less than 5 minutes left.
Oh, okay, right. I need to rush that. I just want to say, I'm going to miss out any mathematics here, but just to say, we actually deliberately perturb initial conditions, or we add initial perturbations or project initial perturbations onto dynamically unstable directions of the forecast flow, things called singular vectors, to try to, if you like, add some extra oomph or some extra growth to perturbations, because if we didn't do that, we end up with underdispersive ensembles. So this issue of how to represent uncertainty is not, I would say, a solved one in meteorology, even though we have progressed enormously in 30 years. I'm going to finish. This is my very last slide, actually, so I hopefully have time for a couple of questions. I heard a little bit about multi-model ensembles using multiple models. And they are used a lot, actually, in climate change projections and seasonal forecasting. So, for example, in the IPCC climate change reports, we had one last year, big one, they make up their projections from multiple models. And, you know, there's a certain amount of good work done in that area. And I often wonder whether the WHO could coordinate a global multi-model ensemble for epidemics, much like WMO, the meteorological organization, does for climate change projections. However, there is a kind of problem in a multi-model ensemble, because typically these individual models are, built by kind of academic groups around the world, and they're typically low-resolution models. And they all sort of suffer from the same class of problem that I tried to highlight above, the fact that they're all got a similar class of parameterizations. They may have variable parameters and things, but they're all working on the principle that subgrid processes can be parameterized. And in fact, you would never use climate multi-model ensembles in weather forecasting mode, particularly for probabilistic predictions of extreme weather, because the coarse resolution would just give you very poor forecasts of extreme weather. And in fact, there's now a big debate in the climate model community as to what the right direction to go is. Should we just continue with some large diversity around the world of relatively low resolution models and have a relatively large ensemble of relatively low resolution models, or whether actually we'd be better off pooling resources to create a smaller number of very high, potentially kilometer scale models, bearing in mind most climate models are about 100 kilometers these days, through a kind of a CERN for climate change center or a federated group of centers around the world focusing on that. And I just wonder if there's a parallel here for epidemic prediction of whether, a few very good models is better than a lot of average models. Again, you can be beguiled by ensemble mean statistics to think that a large number of kind of average models is the best. But if you're looking at kind of trying to forecast the tails of your distributions, which in my case would be extreme weather, you might get a very different picture. So I think I'll stop at that point. Thank you very much.
From the hall, any questions for Tim Palmer? There is one. Here we go. Tell us who you are.
Hello, hi. My name is Kaveh Jahanshoy. I'm a lead data scientist at Data Science Campus, ONS. Actually, the discussion we had here for the type of models that we are using is pretty much helpful, not just for the pandemic that we have been involved in, but for the real-time estimation of mobility or a type of models that we are using for travel to work and validating census, etc., relying on the high resolution or high timely granular mobility data. These type of things are helpful. The questions we have is that we quite often have two dimensions of the type of questions, inference versus predictability, and within them, where the role of uncertainties are. So we have situations like a EU exit, we changed the whole structure of the model. So you cannot, in your Bayesian stats, for instance, rely on the prior, which are tend to build in the future because the structure of your model has changed since EU exit, and then you would have a different type of indicators would have a different meaning compared to what we had before for a regular prediction of mobility, let's say. And then we need the good predictability for which we can rely on non-parametric models, but at the same time, the parameters need for the inference for decision making. So how we can bring these two together when we are discussing about these type of uncertainties that you're dealing with, which, as you well mentioned, is not resolved really.
Yeah, I mean, we're sort of fortunate in, I'm not sure I can give you a very good answer to this question. I mean, we're fortunate in meteorology to think we know the underlying equations, at least as partial differential equations. And I think it's kind of salutary that even in that situation where you know precisely what the underlying equations are, we still have enormous difficulty in actually representing in a kind of rigorous way, I would say, the uncertainties that arise when you truncate these equations. And so I think for me, the sort of message is that when you are, when you have models which are more empirically based, I think, it's really important to recognize that the most likely direction your predictions are going to go is of being overconfident in your predictions, that you sort of underestimate the uncertainties. Because even in a situation where, as I say, we know the equations, we still typically underestimate uncertainties. And we, as I say, we deliberately focus perturbations onto unstable directions to try to minimize that problem of overconfidence. So, and it was a little bit like the last talk, I mean, there was a nice picture from Dr. Edeling of the growth of the ensemble, but actually the uncertainty was completely undermined by the fact there was no representation of initial uncertainty. So I think the message here is one of, being cautious, I suppose, about predictability and our ability to represent that well. I think most complex systems, it's extremely challenging problem.
Thank you for that. Shall I pass on? We've got a couple of it's Jane Leaks here. We've got a couple of questions on the floor here, so I'll just put them through.
Yeah, of course. Yeah. Hi, I'm Tim Russell from the London School of Hygiene Tropical Medicine. I thought that was really, really interesting, and I think we can probably learn a lot from that kind of approach in epidemiological modeling, probably mainly because a lot of epidemiological models do use ensemble means. It's really common. Do you have an idea of how wrong that would be for an epidemiological model? It sounds like you have a good idea for meteorological models, and it's partly because they're chaotic, or at least that's sort of how I interpreted it. But it's less clear how chaotic epidemiological models really are, and if they are, it's sort of more from a theoretical point of view rather than the models that we really fit to data. You rarely see chaotic trajectories. So how sort of wrong is that approach in epidemiological modeling?
I'm not saying it's wrong. I mean, it's not so much it's wrong, I mean, in terms of meteorology, it's typically not a useful thing to at least focus too much attention on, because, people, like in that October Michael Fish storm, people want to know, you know, is there going to be a hurricane? And an ensemble mean would never tell you that. It just smooths things out too much. So, I mean, I suppose the the parallel would be in terms of the government policy. I mean, it was always the case of what is the likelihood of overwhelming the NHS with with COVID cases. That seemed to be the determinant in deciding on policy. So, you know, it's being able to be sure you have a system that can predict the probability of that the number of deaths and the number of hospitalizations, which you could say is sort of more looking at the tails or the extremes of the distribution. It's very similar in climate change. You know, I mean, what really will be a kind of literally a killer for humanity would be if the global temperatures exceed, say, 4 degrees. Now, the ensemble means are very unlikely to get to 4 degrees. So you're talking about estimates of, well, it's not so much tails, but of the chunk of the distribution away from the mean. So that was my point really, that the key things that people tend to be interested in most of the time is the likelihood of things which will be, you know, calamitous and want to avoid. But since Peter mentioned it at the beginning, I just say that it is interesting how those distributions from Dr. Edeling's model, you know, they're very similar in a way to climate change distributions, which are skewed, and that is actually where the ensemble mean, at least, I mean, the fact the ensemble mean lay above the deterministic forecast is telling you that distribution is skewed. But probably what's of interest mostly is it's the tails of the distribution for policy making.
Tim, thanks very much for that. We need to move on. Let's just thank Tim again for a very stimulating talk. The last presentation today here is by Diana Suleimanova, and she's going to talk about the VECMA toolkit and things to do with it, right? And we need to make sure you've got your display available for everyone to see.